This video will show you how to make a carbide driving force heat map. In the video, we will calculate the carbide driving force as a function of two composition variables and visualize the results as heat maps and contour plots. The calculation is based on example T9 of the examples that were included with your software. You can access the example file by going to the Help menu, Examples Files, Thermo-Calc. To begin the example, click on the one-axis equilibrium template from the home screen of Thermo-Calc. The template used to be called Property Diagram, so if you have Thermo-Calc 2019A or older, click on the Property Diagram template. The calculations will be the same, only the name has changed. Select the FE demo database and the elements iron, chromium, and carbon. We will accept the default composition, so make sure your values match mine. When you calculate the driving force of a phase, you always need to change the status of that phase to dormant. To do this, select the Phases and Phase Constitution tab. Here we can see that all the phases are selected. We will be calculating the driving force of the M7C3 carbide precipitate from austenite, so we only need to select two phases, the M7C3 phase and the austenite phase. First, we will uncheck all the phases, then select FCCA1, which is the austenite, and the M7C3 carbide. We will also change the status of M7C3 to dormant, since this is the phase for which we are calculating its driving force. Next, select the Equilibrium Calculator node and set the temperature to 1000 degrees Celsius. Under Calculation Type, select Grid, or select Property Grid if you have an older version of the software. We are looking for the driving force of M7C3 as a function of two composition variables, so we will set those variables in the Axis Definition section. Set the first quantity to mass % carbon with a minimum of 0 and a maximum of 1. We will use the default for the number of steps. Set the second quantity to mass % chromium with a minimum of 0 and a maximum of 20. Now click on the Plot Renderer node. Set the plot type to heat map. The first two axis variables are carbon and chromium, which we set in the equilibrium calculator. Set the third axis variable to normalized driving force. If you have an older version of the software, select driving force. The name was changed to clarify that it is normalized by R times T. Set the phase to M7C3, because that is what we are looking for. Our calculation is now set, so select Perform at the bottom center of the program. Once the calculation is complete, your plot will appear in the results pane. This plot shows the driving force represented in a heat map. High values are represented in red, and low values are represented in blue. The pixels in this heat map are rather large, so to get a clearer view, you can change the interpolation. The higher the values, the clearer the plot will be. I will change the interpolation to 100 by 100 and select Perform again. We now have a smoother plot. However, when you use interpolation, you should always check that the results do not change too much from the non-interpolated plot. In a heat map, each square corresponds to a calculated point. When you interpolate, the program guesses what the points in between should be based on these calculations. This can sometimes give you strange results when interpolating sparse data into a fine grid, so make sure the interpolated plot looks consistent with the non-interpolated plot. Our plot looks fine. You can also change the plot type to contour to get a contour plot for the driving force. To do this, change the plot type to contour. Check the automatic scaling box if yours is not already checked to give us a better view of the results. Then select Perform again. This allows you to see the values represented as lines. If we double-click on the top of the results pane, the window will expand to full screen and we can see the values more clearly. On the left half of the plot, we can see several instances where the driving force goes below 0. From a thermodynamics point of view, when the driving force is negative, the carbide will not form. When it is above 0, it has the driving force to form, but it is not guaranteed that it will form. We hope you found this video useful. We are constantly working to create new videos, so check back regularly at www.thermocalc.com.